Welcome to Heat Transfer Course 1. Introduction and Basic Concepts. Let's begin with the foundation of heat transfer. Before diving into calculations, it's crucial to understand the basic principles that govern how heat moves. Heat transfer is simply the movement of thermal energy due to temperature differences. It always flows from a higher temperature to a lower temperature until thermal equilibrium is reached. There are three primary modes of heat transfer: conduction, transfer through solids; convection, transfer through fluids; and radiation, transfer through electromagnetic waves. Grasping these basic concepts will help you approach any heat transfer problem with clarity and confidence. So never skip the fundamentals.
1. Clarify your learning outcomes. Let's set clear goals for what you'll learn in this chapter. A good learning outcome tells you exactly what knowledge and skills you will gain after completing the lesson. For heat transfer, the focus is on mastering both fundamental principles and practical applications. You will learn how to connect thermodynamics with heat transfer, identify different types of energy, and perform energy balances. Most importantly, you will understand the three key heat transfer mechanisms: conduction, convection, and radiation, and learn how they interact in real situations. A strong learning outcome should guide you through theory and practice, helping you solve real-world heat transfer problems with confidence. 2. Distinguish thermodynamics from heat transfer. Let's clarify a common confusion. Thermodynamics and heat transfer may seem similar, but they focus on very different aspects. Thermodynamics helps you calculate how much heat is transferred during state changes, but it ignores how fast the transfer happens. It's all about quantities in equilibrium. Heat transfer, on the other hand, is all about the speed and method of heat movement. It looks at rates, mechanisms, and how energy actually flows over time. Understanding this distinction is key. Thermodynamics tells you how much, heat transfer tells you how fast and how it happens. 3. Understand forms of energy and energy transfer. Let's break down energy into simple, clear categories. Energy comes in many forms: thermal, mechanical, kinetic, potential, chemical, and nuclear. Each plays a unique role in physical systems. When we talk about heat, we mean energy transfer caused specifically by temperature differences. It flows from hotter to colder regions. Work, in contrast, refers to energy transfer caused by factors other than temperature, like force or pressure differences. Keep this distinction in mind. Knowing what drives energy transfer helps you apply the right principles in heat transfer problems. 4.1. Focus on conduction as a heat transfer mechanism. Let's start with conduction, the most basic way heat is transferred. Conduction happens through direct molecular interaction without any movement of the material itself. It follows a simple rule called Fourier's law. This law shows how heat moves through a solid, depending on how big the temperature difference is, how thick the material is, and how much area is involved. The formula is Q equals negative Ka times the rate of dt dx, where K is the thermal conductivity of the material. Understanding conduction means knowing how molecules pass energy and how to calculate heat flow using this simple but powerful equation. 4.2. Master convection and heat transfer. Next, let's focus on convection. This is heat transfer between a solid surface and a moving fluid, like air or water flowing over a hot plate. Convection is described by Newton's law of cooling. This law connects the heat flow to the temperature difference between the surface and the fluid. The formula is Q equals HA times Ts minus T infinity, where H is the convection heat transfer coefficient, which depends on the fluid type and flow conditions. Understanding convection helps you analyze how fast heat is lost or gained in systems involving fluids. 4.3. Simplify radiation heat transfer. Let's finish with radiation, energy transfer that doesn't need a medium. Radiation travels through electromagnetic waves, even through a vacuum like space. The main principle here is the Stefan-Boltzmann law. It shows how the heat emitted increases rapidly with temperature. The equation is Q equals epsilon sigma AT4, where epsilon tells us how efficiently a surface radiates heat, and sigma is a universal constant. Radiation is often overlooked, but at high temperatures, it can dominate heat transfer. Focus on the key idea. Temperature to the fourth power means small changes in temperature can cause big changes in radiation heat flow.
5. Connect heat transfer to real-world applications. Let's see why heat transfer matters in your daily life and career. Heat transfer is everywhere. You experience it every day without even noticing. In everyday life, it helps regulate body temperature, keeps our homes warm or cool, and prevents electronics from overheating. In engineering, it's essential in car radiators, power plants, refrigerators, and solar panels. Practically every mechanical or energy system relies on it. By recognizing these applications, you'll understand why mastering heat transfer gives you practical skills that are useful both in life and in engineering practice. 6. Know the history of heat transfer. Let's explore how the understanding of heat transfer evolved. In the early days, the caloric theory imagined heat as a fluid-like substance that flowed between objects, but this idea was later rejected. It was Count Rumford and Joule who changed everything by proving that heat comes from molecular motion, mechanical energy converting into heat. Finally, the development of Fourier's law gave us the first scientific method to calculate heat conduction. Knowing this history helps you see heat transfer as a science built on experiments and discoveries, not just equations. 7. Understand heat transfer equipment and problems. Let's end by connecting theory to real equipment. Heat transfer equipment is everywhere. Think heat exchangers, boilers, condensers, furnaces, and cooling systems. When working with these systems, you'll face two main types of problems. First, rating problems. Here, your job is to calculate how much heat is being transferred by an existing system. Second, sizing problems. This is where you design or select equipment big enough to handle a certain heat transfer rate. This distinction is simple but crucial. Always know whether you're evaluating performance or designing capacity.
8. Apply energy balances and the first law of thermodynamics. Let's wrap up by linking heat transfer to the energy balance principle. The first law of thermodynamics tells us energy is conserved. It's just transferred or transformed. In a closed system, the rule is simple. Q minus W equals delta U, where Q is heat transfer, W is work done, and U is internal energy. For steady-state control volumes, like engines or turbines, we add mass flow to the equation. Q dot plus W dot plus M dot H equals constant. Mastering these balances helps you track energy flows, ensuring your systems obey the basic laws of physics.
9.1. Know thermal conductivity for better design choices. Let's talk about one of the most important material properties in heat transfer, thermal conductivity, symbolized by K. Materials with high K values are excellent heat conductors. Think of metals like copper and aluminum. They let heat flow quickly and efficiently.
On the other hand, materials with low K values are good insulators. Examples include air, rubber, and styrofoam, which block heat flow and help keep things hot or cold. Understanding K helps you pick the right materials, whether you want to conduct heat fast or slow it down. 9.2. Focus on thermal diffusivity to predict heat speed. Let's explore thermal diffusivity, symbolized by alpha. This property tells you how fast heat spreads through a material. Thermal diffusivity combines three things: thermal conductivity, K, density, ρ, and specific heat capacity, Cp. It's calculated as alpha equals K divided by ρ times Cp. A high alpha means heat spreads quickly through the material, while a low alpha means it spreads slowly. Use alpha when you want to predict how fast temperature changes will travel through solids, which is especially useful in transient heat transfer problems. 10. Understand simultaneous heat transfer in real life. Let's conclude by recognizing that real-world heat transfer rarely happens in just one way. Multiple modes usually happen at the same time. For example, in a heated pipe, conduction happens through the pipe wall. Convection happens between the outer pipe surface and surrounding air. Radiation transfers heat from the pipe to the environment. This means you must analyze heat transfer holistically, not in isolation. Successful engineers always account for these simultaneous effects to design efficient systems. 11. Use a simple, structured problem-solving approach. Let's wrap up by learning how to solve engineering problems in a clear, step-by-step way. Start by understanding the problem. What are you being asked to solve? Then, draw a schematic to visualize the setup. Next, state your assumptions to simplify the problem and apply physical laws like conservation of energy. After that, find the right properties from tables, perform your calculations, and finally, interpret and verify your results. Following this structured approach keeps you organized and increases your chances of solving heat transfer problems correctly. 12. Always follow engineering codes and standards. Let's emphasize the importance of codes and standards. In engineering, safety and efficiency aren't just suggestions, they're mandatory. Organizations like ASME, ASTM, and ANSI create rules to make sure equipment is designed and used safely and efficiently. These standards cover everything from heat exchangers to insulation to materials. Following them isn't optional. It's a basic responsibility for every engineer. By using these codes, you ensure your designs meet legal requirements and protect people and systems from failure. 13. Be careful with accuracy and significant digits. Let's talk about a simple but crucial point: accuracy. Every calculation should match the accuracy of your input data. Don't use more decimal places than you actually have. Always apply proper precision in your answers. Using too many digits makes your answer look falsely accurate, which is misleading. Good engineering practice is about being realistic and honest in your results, not pretending your answer is more precise than your measurements allow. 14. Explore special topics in heat transfer. Let's look at a few special topics that connect heat transfer to real-world comfort and energy efficiency. Thermal comfort is crucial in daily life. Most people feel comfortable between 23 to 27 degrees Celsius with 30 to 70% humidity. Energy loss and cost analysis is a major concern in engineering. Uninsulated surfaces lead to significant energy waste, increasing costs and emissions.
Lastly, super insulation, like aerogels, offers cutting-edge solutions. These materials have ultra-low thermal conductivity and are used in high-efficiency insulation systems. These topics remind us heat transfer is about people, costs, and technology.
15. Wrap up with a clear summary. Let's summarize the key takeaways from this chapter. Heat transfer is different from thermodynamics because it focuses on how fast energy moves, not just how much. You've learned the three main modes of heat transfer: conduction, convection, and radiation, each with its own governing laws. Finally, understanding energy balance and heat transfer laws helps you design efficient thermal systems, whether it's in everyday life or engineering projects. Remember, these basics are the foundation for solving real-world heat transfer problems.